Stop talking.
I'm going to talk today about my fourth FPGA synthesizer. For background, this project actually is 2 years in the making. It has its genesis in a kind offer that Christopher Lazinski made on birthday 2023, in which he offered to anyone interested a Pico Odds board, and he, after some debate, he decided to hand it to me because I said I'll at least put E4, my E4 on it, which I did. That actually happened all the way early December. But what really excited me about this board is that it not only has a Raspberry Pi Pico CPU on it, it also has an ICE40 FPGA on the same board, and it exposes all the pins, and most importantly, it exposes several of the key pins to control the FPGA to the CPU, so that you have an environment that where the one can manipulate the other. This is what the board looks like. The purple pins are the Raspberry Pi pins. The redder pins are the pins for the FPGA. And of course, this ICE40 has a large sea of lookup tables, four input lookup tables. It has a bunch of RAM on the FPGA. It has some additional dual ported RAM. It has some BSP blocks, and it's interestingly part of a larger family with a similar structure. But the other cool thing about it is it happens to be one of only a handful of FPGAs where the open source community has figured out the format of the bit stream, so that you can do stuff with it. And they've been, generously communicated all sorts of documentation. They built simulators. They built synthesis tools of their own. They built web-based tools. We can view layouts, all sorts of cool stuff. So this is what the device looks like. It's got a grid of say 26 by 32 cells in it. On this particular, there's a whole family, and in some of them, the sides have things attached. But in this one, most of the meat of the I/O pins is hooked up to the top and the bottom, the cyan ones here. And then the purple elements are just logic elements with the lookup tables. And then these yellow bands are a mixture of DSPs and the RAM. So inside of one of those purple cells, this is what it looks like. You got 8 separate lookup tables. They're structured in a way that you can configure them to do an arbitrary lookup table with 4 inputs. You can also arrange to attach a flip-flop that's optionally there for each of them, and then there's a way to route carries into them. The tantalizing thing, of course, about the config is it is just a gigantic bitmap. So it's 1300 something by 512. It's actually chopped up when you feed it to the device. It's actually done in 4 banks, and you have to sort of tell it, okay, here's bank 1, and then they're, for whatever reason, lopsided. On some of the device types, they're symmetric, but this particular one has the slices there are not the same size. And all one has to do to get it to do an interesting thing is to feed it the appropriate set of bits. Easy problem, right? The routing within the system is very regular. So each of the individual blocks are just mirror copies of each other. There is a sea of routing that has this kind of complicated grid pattern. It basically has 2 sort of tracks to it. One that has a set of stands that go up 4 steps, and then both vertically and horizontally, and then another set that go up 12 and vertically and horizontally. And for the ones that go 4 steps, they sort of slide over 12 elements at a time. For the ones that go up 12, you kind of only get 1 new bit exposed each time. And then there's this opportunity for things to look to the guide to the right of them as well. In addition, not displayed here, there's the ability to route things to neighboring cells, so that from one cell you can sort of see into each of the neighbors. the bitstream format was complicated. I spent a colossal amount of time wrapping my head around it, despite all of the material out there. There's some output from the tool. I spent a ton of time, pencil and paper, looking at, if you can imagine, individual routing things. That the approach that the open source community took is a reasonable one. That if you're not trying to sort of do it in a simple way, they approached it as a database. They have a giant database that they've emitted that captures here is all the routes in the thing. This obscures the structure that's present. And so it took me a long time to understand it. I tried many different approaches. I tried this is thrown into graph as sort of all the routes within one cell. Not helpful. Finally, I hit upon visualizing sort of the relationships between individual pins within the config block for one cell and color coding them. And I originally planned to like print this out on some poster and stare at it, giant pages, but I found I was able to pan around. To give you some idea, there's little chunks of config where there's an enable and then some number of selection bits to choose which out of a set of different possibilities get routed from one of these to a particular position. And and then there's also a section that describes the bits for the lookup table. And then but then ultimately what you care about is the following, which is routing from an output. The structure basically has that you can route from you want to be able to feed an output to a local group for each cell, of which there's 32 of them, with this particular number between from the into each of the four inputs or each of the lookup tables in the bits, and then from there you can get to one of these spans. And the spans then circle back and you can route things in. There's also some globals that I've only partially implemented. This is where I was about September, and I had some stuff that I showed off then, but that only gets me the logic cells. I needed the I/O pins to be able to do anything. And the I/O pins had, unfortunately, an equally complicated scheme, well, almost equally complicated, where to go from an input pin, you have to come in, and then there's a way to route it either to the spans or, as I discovered literally last night due to a misunderstanding, a way to get directly to the neighbors. The pins that are going out, you go from an output span into one of these local groups and then out to the pin. And there's a whole separate sort of set of config bits that's different in each of those. To represent all this in Forth, I had to come up with a way to represent these. I wanted to represent these as objects because it's like a sea of nodes in a graph. A lot of complicated rules for traversing them, where you're sort of going from one type of wire to another. And so I approached this by coming up with a special object-oriented framework that let me use only the storage in one cell to represent each element, but treat it like an object. And this is a great example of a thing that only Forth can do, where you're able to sort of reconstruct your object-oriented framework to do the thing you need it to do. There's a whole separate talk. Very briefly, what I did to make this work is that for each individual sort of output wire, local group, all the different things I mentioned, there's an interface where you can create one. You can count how many different options are there as to how this thing could route. You can set which option is routed. You can find out which option you're currently routed to, or you can find out where does that particular selection take you to. And so that's all. And then I also have a print method because goodness knows I needed to print. That allows this simple routine to route from a source to a destination. So whenever I want to go from one place to another, I just have to check: am I already where I need to be? Then I'm done. Otherwise, I see if the particular destination already has something routed into it, in which case that's my only option, and I check to see if that's a valid path. Otherwise, I find out how many other choices do I have. loop through each of them, try them, go down the path and see if I can find a pathway there. If not, I backtrack and see if I can find my way. So just a brute force, exploration of the routing space. With that, as I mentioned back in September, got me to the point that I could have elements, route them between different places. It's interesting the patterns that you get in terms of, here I'm going from, different, the outputs to down various different routes. The I/O pins look fairly similar. There's unfortunately two I/O.
Change the focus of the camera so we can see what you're pointing to.
Oh yeah, let me do that. There we go. Each of the I/O cells has potentially, although not all of it, they're very non-uniform in terms of how the I/O pins are attached. They have up to two pins that are connected to them, and those pins are each generic and can be configured as an input or an output. There's configuration bits for what's the pull-up resistance and a bunch of fun stuff. But ultimately, I was able just literally late last night to get this working. Well, so I thought I had it working until I tried it on the device circa yesterday-ish, or the day before yesterday. And then on the actual device, the outputs pins seemed to work, but the input pins did not. They just got zeros. Turns out I had a thing flipped. For some reason, something labeled in the docs as a 0 and a 1 were inverted. So that was my issue. And so let's briefly look at what the synthesis language looks like. There's sort of a low level and a high level. The low level, you can get an individual LUT. You could take in 4 wires and a lookup table and do the output. You'll notice the flip-flops are not in there because I haven't gotten to the flip-flops yet. So I just have gates right now. I have the ability to route in an input pin and get a wire out for it, or then take an output pin and route a signal that I brought to it. I have this abstraction of a bus where I can combine multiple wires into a bus and then pull wires back out of that bus. And built on top of that, I can then, built on top of the LUTs, I can then build each of the basic kinds of operations. Zooming up slightly higher level, I have the option to specify as I'm allocating LUTs where they get placed. So I can sort of say, well, I want to start allocating them in this spot, because sometimes you can get yourself in a corner where you can't find a pathway because I haven't exposed all of the different routes that are possible. And then a way to get a batch of input pins and a batch of output pins. I have the plumbing in place to create flip-flops in the register. What I haven't hooked up yet is the enable and clock pins, which are the one blocker there. In principle, it's very close, but I said that about the I/O pins. And then built on top of those, I have versions of the major logical ops that take a bus in and can do an AND across a 16 element thing, stuff like that. So for example, here, place at a particular cell, a register, put its object in a value, create another one, then you can maybe go to another location, feed that whole register's output through an inverter, give that a name. Same with the other guy, maybe feed both of those into an XOR and give that a name. That's sort of what the synthesis language looks like. It's the whole thing is taken, relatively small, a little over a few thousand lines. I've just pushed that out on the Micro eForth site. My demo is the most colossally difficult to acquire a single inverter because that's until late last night I did not actually have it working on the real device. So this is what it is. It basically, you have a single input pin coming in that gets fed to an inverter. It then gets fed into the inverted pin gets fed into there's a blue LED on the device. The uninverted signal gets fed into the red LED. And that is what it looks like when laid out. You get the input pin coming in here. It gets sent into this just pass-through LUT. From there, it gets fed into the inverter. And then the inverter goes all the way over here through this pass-through LUT up to here. And then the other copy of it goes around here and then out to that pin. So with that, I'm going to pop out to a demo. And that's not going to work with the video connected. All right. Tell you what.
Can you tell us about it?
I'm going to tell
Do
you
a more complete talk in December.
I will do a more complete talk in December. Demo. Okay. Everything. But anyways. So the net is that you hook the thing up. Interesting thing about the things that I would have shown with the console. There are commands, from the CPU to turn on the FPGA and enable it. By default, the FPGA will boot up and load from it. There's a separate piece of flash that it will load from. So it will turn on, and there's I programmed it long ago into the flash a blinking thing. What I would then show you is running the synthesis. It's very slow on the device. One thing that I did not account for is that it was a little slow, a little pokey because of all the pads on my desktop. It's very slow on the thing. So that little program that I just showed takes an order of maybe 30 seconds to run to synthesize those gates because it's exploring all the pads. Lots of things I could do to maybe make that faster. For one thing, it's exploring sort of the full tree of possible paths at each branch, and it's not early outing in cases where it's sort of routing the wrong direction. So it'd be best if I sort of made sure it's at least going the right direction as it routes, or else that's going to be slow. So lots of things missing. As I mentioned before, the flip-flops, I have ways to allocate them. I have ways to route things to them, but I don't have ways to route their enables and clocks and sets and resets, which are necessary. I have skipped some of the options for routing. I mentioned those long horizontal and vertical spans. In each cell, there is an opportunity to connect a horizontal span and route it to a vertical span, or vice versa, with a very limited set of combinations. The reason I haven't done those is mostly because then you get the combinatoric explosion of all the top paths, whereas currently you sort of have a bounded space of places that you consider when you're routing. I have not routed the chip-wide globals either because those have some goofiness. There's some weird cells in one spot that you have to set up just so. And then there's all sorts of other stuff on this chip. There's phase lock loops you can set up. There's that dual ported RAM, and there's a DSP on the chip as well. So with that, I'll take questions, or I have no idea.
You got a couple minutes.
Yeah.
A comment on the FPGA.
Yes.
It is a more or less uniform sea of cells, right?
Yes.
The first FPGA I could actually work on back in 30 some odd years ago was QuickLogic, which was a anti-fuse FPGA. So it wasn't really field.
Yeah.
And it let me, that was the only one I could think in. Everybody else, Xilinx and everybody had these complicated cells. And the sea of uniform gates, like you found, it was wonderful.
Yes. Interestingly, one fascinating thing I found comparing my layout, and it shows off best in like this picture. If you the things you get out of the conventional synthesis tools are just a random garble of stuff.
Exactly.
Whereas if you my tool, one nice thing is because I've got this little bit of additional control about where it sticks it, you get these nice patterns of how it's spread. That said, you could also get into a situation where, oh no, I'm out of pathways out of to where I want to go. So
I arranged them in a nice regular bus order, made it organizable. When I had the optimizer, what I found was they had the bits scattered all over the place, everything optimized in bit clumps rather than in register wire clumps.
Yeah. There's all kinds of, like, one other thing that the synthesizer I noticed was new. You got a 4-input LUT. Well, you can permit those inputs, right?
Yeah.
So that it will happily do that if it thinks it will find a free route from it. So, and with that, I'm at time, and
Give me a short break while we figure out the technical aspects of getting sound on the air. Do we need to turn off the speakers in the room?
No.
All right.
Want the camera zoomed in on you or?
You can if you want.
It's on you.
I have no.
Are you gonna be gesturing at the screen is I guess.
If you want to gesture on the screen, use your Windows mouse pointer.
That's what I'm gonna do.
You're awesome. It's just like Zoom, except we're all here. So what's set up professional audio and audio settings on the screen? Can you make that go?
I can try.
It's not mission critical.